Okay, in section 2.1, what we're going to look at is we're going to take a closer look at polynomial functions, okay, and also power functions and rational functions. So starting out with polynomials first, we have dealt with some polynomials already in this class, and also some in Algebra 2 as well. Okay, but ultimately the definition of a polynomial function, okay, it says let n be a non-negative integer. Okay, so we're going to have coefficients a sub 0, a sub 1, and so on. Okay, and what it boils down to is these numbers they can represent really any number that we want to, but the powers on the x's here are going to be whatever power the highest one is. Okay, it could be x to the 1, could be x to the 5, could be x to the 200. Okay, but ultimately when we put these power functions together, okay, into an addition or subtraction of a number of terms here, okay, then we have what we call a polynomial. Okay, so the key issue here is that we have something of the form ax to the n. Okay, and again, plus or minus another ax to some other n, etc. And again, we could have any number of terms here. We could have one term, we could have two terms, we could have 200 terms. Okay, the powers could be anything. They could be 0 power, could be 1 power, could be 900 power. Okay, so a couple of vocabulary words involved in this, though, is that if we have a polynomial function of degree n, okay, whatever the highest power is, that's going to be the degree of the polynomial. Okay, and then whatever the a of n is, which is the number in front of the highest power term, okay, that's what we're going to call our leading coefficient. So all the numbers in front are going to be called coefficients. The leading coefficient is going to be the one that's the number that's in front of the highest power term. Okay. We can have a function that is just f of x equals 0. We know if we graph that, that would be the x-axis. Okay. And that is a polynomial function also. Okay, it has no degree and no leading coefficient. Okay, because again, there's no x term here. Okay, and the degree of it, okay, we'd say it has no degree, it has no leading coefficient. Okay. Now let's take a look at a couple other. There's a couple in your book I want to look at here on page 170. Okay. There are some polynomials here in this example. Okay. So I want to make sure we understand the difference between a polynomial and a non-polynomial. So starting with a, we have 4x to the third minus 5x minus 1/2. Okay, this one is a polynomial because we just have numbers in front of x's with powers that are positive. Okay, in this case, same thing. We have 5x term. We have a 1/2 negative, of course, as our constant term. And so we would say that this is a polynomial. It's got degree 3. The leading coefficient is 4. Okay. And that would be that. Now, when we look at part B, here's the difference. This is not a polynomial because the power is negative 4. Okay, the powers here, in order to qualify as a polynomial, the powers on our x's have to be positive. Okay, or they could be 0, of course, because 1/2, if we wrote that with an x, would be x to the 0. Okay, so this would not qualify as a polynomial. Okay, part C would also not qualify. Okay, if we didn't have the square root sign on that whole thing, then we would say, yeah, it's a polynomial. If we just looked at the 9x to the 4th plus 16x squared, that would qualify. But this does not because of the fact that we have that square root sign. Okay. In part D, we have 15x minus 2x to the 4th. This would qualify. All of our x's have positive or 0 powers. Okay. I wouldn't say this is in the right form, though, because it's not written in the highest power down to the lowest power. In the standard form, we always want to write the highest power first. Okay, identifying the leading coefficient here, we have to be careful if it's in like this, because we might say the leading coefficient is 15, but it's not, because remember the leading coefficient is whatever is in front of the highest powered term. So in this case, our leading coefficient would be negative 2. Okay. Now, let's look at a couple of different types of polynomial functions. There's a list in your book on page 171 also that has the same information. Okay, I'm going to add to this a little bit from what's in your book as well. Okay. So again, these are some common polynomials. We have a 0 function, again, f of x equals 0. Okay, the degree is undefined. Okay, we don't say that's degree 0. We say it's degree undefined. Okay, again, there's no leading coefficient either. Okay, if we have a constant function where f of x equals a and a does not equal 0, so a could represent any number here. It could be f of x equals 5. Okay, that would be a constant function. Okay, we'd say the degree of that is 0 because like I said earlier, okay, this would be the same as writing 5x to the 0 power, because x to the 0 would just be 1, and we'd be left with just 5 only. Okay, so that's why we say it's degree 0. In my case, okay, the leading coefficient part here, okay, this doesn't really, if we consider it to be 5x to the 0, then we could say that 5 is the leading coefficient. It's the only number available to even be a coefficient at this point. Okay. Okay. The next type is degree 1. If we have a degree 1 polynomial, which would be a linear polynomial, we've spent the most time in our math careers dealing with linear functions at this point. So if I put an example down like 5x plus 7, that would be a linear function. Okay. The leading coefficient, of course, being 5 again here. Degree is 1 because the power on x is 1. It's the highest power here. Okay. And then the quadratic function, okay, we've spent the almost equal amount of time dealing with quadratic functions. So if we had something like 4x squared minus 2x minus 3, that would qualify as a quadratic polynomial. Okay. It would be degree 2 because the highest power is 2 here. The leading coefficient, of course, would be 4 because it's the number in front of the highest powered term. Okay. All right. Questions so far? Okay. The other thing that we should recognize too here is how does this relate to the geometry? Okay. If we were to draw the 0 function or the constant function, if I drew f of x equals 0 or f of x equals 5, okay, we should know just by looking at the equations that that's going to produce a horizontal line. Okay. A linear function, we should recognize that that's just going to produce a line, whether it be positive or negative leading coefficient would tell us the slope, which means whether it goes up or down from left to right. And same with the quadratic function. As soon as we see a quadratic function, we should recognize that that's going to give us a what shape? It's going to be a parabola. Okay, so this would be a parabola. And once again, the leading coefficient tells us whether it opens up or down. If it's a positive leading coefficient, it's going to open up. If it's a negative leading coefficient, it's going to open down. Okay. As I mentioned, I'm going to give you some more names here too, because right now we have constant, linear, and quadratic. Okay. I'm going to give you a couple more names here. The next one is going to be a cubic function. Okay. A cubic function is going to be of the form very similar to this, but we write ax cubed plus bx squared plus cx plus d. So again, the cubic function is going to have a cubic term, okay, where we have the third power. The next one is a quartic function, which is of the form ax to the fourth, bx cubed, cx squared, dx plus e. Okay. So quartic, Q-U-A-R-T-I-C. And then finally, the only other one that has a name for us is going to be quintic. So a quintic would be ax to the fifth plus bx to the fourth plus cx to the third plus dx squared plus ex plus f. So anything that's of that form where we have a fifth degree term. Okay, highest power here is 5, so therefore we call that a quintic polynomial. Any questions on any parts of the naming at this point? Alright, what we're going to look at next then is we're going to spend some time looking at specifically linear equations, linear functions, and reviewing some of the things that we know about dealing with linear equations. So the first part here, they asked us to write an equation, okay, such that f of negative 1 is 2 and f of 2 is 3. So what I want you to recognize first then is for this linear function, okay, that if they tell us that f of negative 1 is equal to 2, that's really giving us a point, whoops, that lies on that line. Okay, putting in a negative 1 into the function gives us 2. That's a point. Also putting in a 2 gives us 3, so they really gave us what? 2 points. So we got 2 points here. Now, if we're going to write an equation for this linear function, okay, we talked earlier about the fact that the best way to write an equation for any line is to start out with the point-slope form, okay, and then all we need is a point and a slope. So I would find the slope first. We know that the slope is y2 minus y1 over x2 minus x1. So we'll find the change in y over the change in x. In our case, it would be 3 minus 2 for the y coordinates. 2 minus negative 1 for the x-coordinates. And so I'd have a 1 on top and a 3 on the bottom, so my slope in this case would be 1/3. Okay. And then the other issue here is if I'm going to put in my point, the question is which point do I use? And the answer is it doesn't matter. You can pick whichever point. If both of those points are on the line, you can pick whichever one you want to. Okay, you can use negative 1, 2, or you can use 2, 3. So I would choose 2, 3 because just because I felt like it. Really no other good reason. Okay. But if we put our 2 in for x1 and our 3 in for y1, okay, we're done. Unless it tells us to write it in a certain form, okay, leave it in point slope form. Okay. Don't change it to any other form unless it tells you to do so. Okay. All right. Now, on your Math Excel homework, however, if they ask you to put the equation in there and they give you y equals and then you have to type something, then of course you're not going to be able to leave the 3 over here. You're going to need to move that to their side. True? Okay, so if it says y equals, then you need to solve for y. Okay. So remember, again, like I said earlier, okay, you could use either one of these. So if I did y minus 2 equals 1/3 and then x plus 1, okay, which one of those would be the right answer? Both. Okay, they're both the right answer. And if you distributed and then added the 2 and the 3 to both sides, they would turn out to look exactly the same when you write them as y equals mx plus b. Okay, as long as you did the math right, of course. Okay. All right. Questions so far? Okay, a couple other things I want to look at here regarding linear functions. And this really doesn't even have to be necessarily for a linear function. Okay, this idea of an average rate of change. Okay, and the average rate of change for any function, okay, between two x values, okay, is f of b minus f of a over b minus a. Okay, I want you to notice that when we look at the values here, the a and the b, those are both x values, and notice they're on the bottom. Okay, they're both x values and we're subtracting them. And remember, if we put x's into the function, we're going to get y values. So really, what is this average rate of change? If I look at it that way, it's y2 minus y1 over x2 minus x1. All it is a what? It's a slope. Okay, it's a slope between 2 points. Okay, so that average rate of change, all that is a slope between 2 points. Okay. All right. So one of the things that we could do with the rate of change, meaning average rate of change, of course, when we do that with a line, we just did it a few minutes ago. If I were to just pick 2 random points on the line and calculate the average rate of change, okay, I would just calculate the slope, and that would be that. True? One question though is, could I do that with another function, like say a parabola? Let's say I knew the parabola went through 0, 0, and I also knew it went through 2, 4. Okay, could I calculate the average rate of change between those 2 points that are on that curve? I got 2 points. Finding an average rate of change is just finding a slope, isn't it? Okay. And so if I did 4 minus 0 and 2 minus 0, I would get an answer of 4 over 2, that is, which is 2. So for this parabola, my average rate of change is 2. Okay, and notice geometrically what that is that I've just calculated. All I did is I calculated the slope between the 2 endpoints, didn't I? Okay, they gave us 2 endpoints to work with. Okay, all we're doing here is calculating the slope between the 2 endpoints, and that gives us our average rate of change, because that's all our average rate of change is it's a slope. Okay. All right. There's one other definition here in your book. It's on page 172. It says a function defined in all real numbers is a linear function if and only if it has a constant non-zero average rate of change between any 2 points on its graph. Okay, so this is just another feature of a linear function. Okay, it's a linear function if we can actually calculate a slope. Okay. Now there's one other type of line here that we might want to think about. Okay, and that's what if I had f of x equals 5 like I had earlier. Okay, that's a constant function, which is ultimately graphically still linear. But if I were to pick any 2 points on that, okay, and calculate the slope, okay, I would get a slope of 0 here. Okay. Now, if I looked at the other type of special line, which is a vertical line, okay, one of the questions here says a function defined in all real numbers is a linear function if and only if it has a constant non-zero average rate of change. Okay, so when we said non-zero here, that's why this does not qualify as a linear function, because what's the slope of this line? It's 0. Okay, so in order to qualify as a linear function, we have to have a constant non-zero slope. So this does not qualify as a linear function. It's got its own designation. It's a constant function. Okay, why would this horizontal line also not qualify as a linear function? First of all, is it even a function? Does it pass the vertical line test? No. So is it even a function to begin with? So therefore it wouldn't qualify as a linear function then either, would it? Okay. And remember, when we have 2 points where we wind up with 0 on the bottom, okay, if we were to calculate the slope between those 2 points that I have marked, okay, we'd have 0 on the bottom, which means undefined. So be careful of the difference between a horizontal line with a slope of 0 and a vertical line has a slope not of 0 but undefined. Okay. Questions so far?